What's up, everybody? In this video, we're going to describe the subatomic structure of atoms. We're going to look at isotopes and then several notation styles, including isotopic notation, periodic table symbols, and hyphen notation. Let's get started by taking a look at what is inside of an atom. Here we've got a picture of a carbon atom with some important things labeled, like the nucleus containing protons and neutrons. In carbon's case, it's got 6 protons, and this particular carbon happens to have 6 neutrons. Those protons and neutrons each have equal masses of 1 AMU. AMU stands for atomic mass unit. Surrounding that nucleus, there are, of course, electrons arranged in various energy levels. Electrons' masses are so small that it's essentially 0 AMUs, negligibly small. So let's talk about what makes this an atom of carbon. Like, why is this carbon instead of oxygen or iron or something else? Is it the 6 protons, the 6 neutrons, the electrons, the 2 rings of electrons, or something else altogether? If you've never learned this before, it's actually the protons. The fact that this atom has 6 protons is literally what makes it carbon. That means if I gave it another neutron, so now it has 7 neutrons, it's still carbon because it still has those 6 protons. I could give it a whole other neutron, still carbon because it still has 6 protons, and that goes for electrons too. If I threw some more electrons in there, it's changing other aspects of this atom, but it's still staying an atom of carbon. That's one of the key ideas for this video. The number of protons determines the type of element an atom will be. So let's get a little bit deeper here and talk about isotopes. Keep that key idea in mind. The protons determine the type of element as we look at 3 different carbon atoms. And right off the top, that's a clue. These are different carbon atoms. So here's my 3 models that I'm going to use. Because they're all carbon, they're all going to have 6 protons. The difference between them will be the amount of neutrons. The first one has 6 neutrons, and 7, and then 8. And you're starting to see what makes these isotopes of carbon. If you haven't figured it out yet, let's put some additional labels in here. This one on the left would be referred to as the lightest isotope because the 6 plus 6 gives it a total mass of 12. We're not even considering electrons, right? Because electrons have essentially 0 mass. This one's a little bit heavier, and this one is the heaviest isotope out of the 3. So what about the electrons? We haven't addressed those at all. If I put in some electrons here and gave this one 2 extras in the outer ring, this one 3, and this one 4, now they all have different quantities of electrons too. None of that mattered because electrons do not affect an atom's isotope status because they do not change the mass, right? Let's just reference these AMUs one more time. Electrons have no mass, so they do not make these atoms isotopes of one another in any way. So let's close this up with a definition of isotopes and what they are. Isotopes are atoms with the same number of protons, but different numbers of neutrons because the electrons don't matter. You could also define this a different way. You could say that isotopes are atoms of the same element, but with different masses. These are like 2 definitions that essentially say the same thing different ways. 2 other vocabulary words that we're going to need before we close out this lesson is atomic number. That refers to the number of protons in an atom. This particular carbon atom has an atomic number of 6. The atomic mass is the protons plus the neutrons added together. This particular carbon has a mass of 12. 6 plus 6 will be 12. Because the electrons have no mass, they're not added in there. And there's the recap of those values. The real goal of all this information is understanding the different symbols and notations that scientists use to describe atoms. That's really what this is all about. So the first type we're going to look at is called isotopic notation, and it's often symbolized with this format or these symbols XZA. In isotopic notation, the X is the atomic symbol. That's what you see on the periodic table. For example, C for carbon, Li for lithium. The Z is the atomic number. That's the bottom left. So that's what you have to remember with isotopic notation, that the bottom left is always the amount of protons. And then, of course, the top left is the atomic mass. That's the protons plus the neutrons added together. So here's that information as a reference. Here is a model of a fluorine atom. See if you can put together the isotopic notation based on this model. You can pause the video to try that before clicking play again to watch me go over the answers. Assuming you've done that, you should have counted the positive, the red ones, the protons, as 9. So on the bottom left, I'm going to put the number 9. If you counted the green particles, probably the neutrons, there was 10 of those, and 10 plus 9 gives us an atomic mass of 19. The electrons here are, as far as you know right now at least, are not going to factor in any way to either of these numbers. So the last thing I need is the symbol of this atom. And if you look up what atom has 9 protons, you'll see that it's fluorine, whose symbol is capital F. So we'll close it out with a capital F. You can also do this in the reverse direction here. I've given you the isotopic notation for an atom, and I'm asking you to tell me how many protons, neutrons, and electrons would be in an atom described this way. Again, you should pause the video and try this yourself first before clicking play again to watch me go over the answers. So here we go. I'll start in the bottom left because it's the easiest one. 17 in the bottom left means it's got an atomic number of 17, which in other words is 17 protons. To get the neutrons, I have to remember that this 35 is equal to the protons plus the neutrons added together. So essentially 35 is that 17 plus some mystery number. So if you do a little bit of math there, 35 minus 17 tells me that there's 18 neutrons. The electrons, technically, we have not even addressed yet, but you might have guessed that in general, unless you're otherwise told, the positives and the negative charges, so the protons and the electrons, generally equal each other. So if there's 17 positive particles, there's going to be 17 negative particles as well. Now you will eventually see that those can change and they can be different, but we have no reason at this point to think otherwise. So with 17 protons, I'm going to guess that there's also 17 electrons. Those are our subatomic particles in this atom. Let's go on to the second type of notation, and this is what you see on the periodic table. I'm going to focus in on the symbol for potassium right here and sort of point some stuff out. First of all, it's got pretty much all the same stuff as your isotopic notation. There's the atomic symbol, the atomic number, and then the atomic mass. One thing you'll notice is that the positions of those numbers are flipped. It's a little confusing to keep track of that, but you'll eventually sort of pick up on the fact that the atomic number is always the smaller one out of the two numbers, regardless of the position. So just be careful that the mass and the number are reversed from where they were in the isotopic notation. The other weird thing about the periodic table is that the masses are given as decimals, 39.098, which is weird. You can't really have, if the mass is the protons plus the neutrons, these are whole numbers, right? There can be 19 protons, but there can't be 19.5 protons. That's not possible. So where do these decimals come from? This actually goes back to something from earlier in this lesson, isotopes. Because the periodic table isn't just describing one potassium atom, it's describing all the potassium atoms in the whole universe. And because the same element can have many isotopes with different masses, they get averaged before going on the table. So in other words, some potassiums might have a mass of 38, some might have a mass of 39, some might be 41. I'm just making these up. The point is, how are you going to represent all those different masses? And the answer is you average them. And of course, when you average things, you can get decimals. The last type of notation is the simplest. It's called hyphen notation, and it looks like this. This one gives only the name and the atomic mass. So that number you're seeing there, 37, is the mass of the particular chlorine atom this symbol is describing. There's no atomic number given at all. We'll sort of understand that when we look at these 3 chlorine isotopes. Notice any similarities? Of course, you showed right off the top that 17 is the same. The atomic number is the same in all of them, right? So hyphen notation says, if chlorine always has the same atomic number, do I really have to put it in this notation style? It says, no, let's leave it out, and let's focus on the only thing that can be different from one chlorine to the next, and that is the mass. So the point is, the atomic number doesn't need to be given. You can use the name of the element and go to a periodic table to look up that 17 if you needed to. So that wraps it up for this lesson on notation, styles, and atomic structure. Thanks a lot for watching.